Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 29. We're continuing with our discussion of continuous distributions part 2. If you watched the supplemental video, which I strongly encourage, we talked about the continuous uniform distribution last time. We calculated its moment generating function, its mean, and its variance. This time we're going to introduce and talk about percentiles and quartiles and then do some examples for continuous distributions. So let's start with percentiles. The 100th percentile is a number, and we use pi sub p such that the area under f of x to the left of pi sub p is p. So what do I mean by that? Well, let's draw a general picture here. Maybe I'll use something we'll learn about, the normal distribution. And it can be anywhere here, whatever p is, pi sub p. That means that the area over here is p. All right, up to that value. So this is the probability that if this is x, x is less than or equal to pi sub p, that's equal to p. And we have that here, and we've written it as an integral here as well. And we can also write it as the CDF of pi of p, of course. Now, the median, here are some special percentiles, and these are also known as quartiles. So the median is pi sub 0.5, and that's also known as q sub 2, the second quartile, or m for median. So we have no lack of ways how to express the median. We have many. Pi sub 0.25, that's the 25th percentile, is also the first quartile. If you think of quarters, if I have a $quarter in my pocket, that's 25% of a dollar. The same thing if I have 3 quarters, that's 75% of the dollar. So Q3 and pi sub 0.75. So let's go ahead and do some examples. We're going to let y be a continuous random variable with a PDF g of y equals 2y, where y is between 0 and 1. Remember that just like for the PMFs, when you do a problem, you need to write down the PDF, and that needs to include the support of x. Find the CDF of y is our first task. So g of y, the capital G of y, is going to be the integral. Since this goes from 0, that's the support of y, is from 0 to 1, then we can integrate from 0 to y. We'll use a different variable. I've used t here. You could use u, you could use x, you could use something else. That's up to you. I like to use t as my integrating variable, just to be consistent. So g of t dt, from 0 to y, and that's going to be, I substitute in for gt, that's 2t dt. So that is, I raise to a power, t to a power, so I raise it from 1, I add 1 to 2, I divide by that new power, so 2, I already have a 2, divide by 2 leaves me a 1 out front, and this is evaluated from from t equals y to t equals 0. I plug in y, I get y squared. I plug in 0, I get 0, so I'm subtracting 0 there. And so I have y squared, where y is between 0 and 1. Now, again, this needs to be written as a piecewise function. So I need to put all 3 parts. This is, so if I have a mistake here, that's a y. So 0 when y is less than 0. Y squared when y is between 0 and 1, and 1 when y is 1 or greater. So now let's find the probability that x is between 1/2 and 3/4 with the same function. So this is going to be the integral of g of y dy from 1/2 to 3/4. We've already figured out the CDF, so we can just use that. We don't have to do the integral again if we've already done it, and we have. So 1/2 and 3/4 are in the support of y, so we can just plug in g of 3/4 minus g of 1/2. And when we do that, that's a square, so we get, remember to take the large number first, so 3/4 squared is 9/16 minus 1/2 squared is 1/4. finding a common denominator, leave it as a fraction. So that means a little bit of fraction work, but that's good for you. Get you used to it. Make sure you have an exact answer. Now let's find the probability that y is between 1/4 and 2. And notice that it doesn't matter whether these are less than and equal to here. With that continuous distribution, you get the same answer. So again, y is from 2 to 1/4, or 1/4 to 2. We take g of 2 minus g of 1/4. Now, what happened here is that where 2 is outside of the support of y. So this is going to be the same as g of 1, which is 1. So that's why this became a 1. And then g of 1/4 is 1/4 squared, which is 1/16. That gives us 15/16. Now we want to find mu and sigma squared. So mu is e of x, which is going to be, in this case, y, f of y, dy. And the integral over the entire support of x, 0 to 1. And so if I have y squared here, so 2y squared integral, I have the squared, I add 1, that gives me the cube. I divide by that 3, I had a 2, so I have 2/3 y cubed. And I'm evaluating from 1 to 0, so this is going to be 2/3 1 cubed minus 2/3 0 cubed. That's 0, so we're left with 2/3 times 1 cubed, which is 2/3. Now, ex squared is, I wrote x. These should be y's. Since we're using y, let's not confuse it with x. Sorry about that. Just a habit of saying x when it's supposed to be the variable that you're doing. So ey squared is, I put in y squared. So y squared times 2y, and then that's f of y, or g of y, and then dy. And so I've got 2y squared, but now instead of y, I put in y squared. So y squared times 2y is 2y cubed, which is what I have here. I integrate that, I get y to the 4th, I divide by that 4, and so 2 divided by 4 is a half. I evaluate from 0 to 1. When I plug in 0, I get 0, so I have 1/2 times 1 to the 4th, which gives me a half. To find the variance, I need ey, this was ey squared minus e of y quantity squared. All right. And so I plugged in for ey squared, e of y quantity squared, do my math, I get 1/18. Now let's find the median. So what we do here is we put p, remember, this is p, equal to, and then we do the integral from the lower value, whatever that is, up to pi sub p, and then we'll do f of y, in this case, dy. And so I don't know why I switched this to t squared. This should be y squared. So y squared from 0 to pi 0.5, and this is 0.5, is going to give me pi sub 0.5 squared. And that is equal to, remember, 0.5. So if I want to solve for pi sub 0.5, it's going to be the square root of 0.5. And remember that f of negative square root of 0.5 is 0 because it's outside the support of y in this case. Let's do another example. Let's look at the absolute value of x. So the absolute value of x here as f of x, and let x be between -1 and 1. It's very handy to graph this. I strongly advise you to graph anything that you can. And so by looking at this, we can look at the area under the curve. We can see that this is symmetric, okay? So, which is handy to know. Anytime you have symmetry, you can use that. So we want to find the probability that x is between -1/2 and +3/4. So we can write the integral using f of x dx, But let's use the definition of the absolute value. That's important. You have to do this when you're integrating the absolute value of something. Remember that when the quantity inside the absolute value is negative, you use the negative of the value. And when it's positive inside the absolute value, use that whatever is in the absolute value. So it doesn't have to just be x there. You could have f of x. And then, so f of x is equal to negative f of x when f of x is less than 0. Sorry, I got scrunched up there. Or f of x when f of x is greater than 0. All right. So we break this out, and on the interval where x is negative, from negative 1/2 to 0, we make this negative x dx. And on the interval where x is positive, we make it positive x dx. And so we evaluate this integral, and we end up with a little algebra and basic math, we end up with 13 over 32. I hope you'll take time to work through that on your own and make sure you understand it. Now, let's find the mean and the variance. So here we have to have x times f of x dx. And again, we need to break this up over the interval where the value inside the absolute value is negative and whether it's positive. And when we do that, we'll have x times negative x, which is negative x squared, and x times positive x, which is positive x squared. We evaluate that, and we end up with 0 for the mean. We then do the same thing for x squared. Please look through that, make sure that you understand what's happened. And we end up with positive 1/2 here, and so the variance is 1/2 ex squared minus ex, quantity squared, which is 0, so that is 1/2. And then we're going to find the pi of 0.25, the 25th percentile, or Q1. And so, again, we do the integral from negative 1 to pi 0.25. And looking at the symmetry, we notice that since half of the area is in the negative, 0.25 from the left is definitely going to be a negative value. So we know that we're in the negative interval here, and so that makes it easy for us to do this. So we use the negative value of x, we integrate from negative 1 up to this value, we solve, and we end up with pi of 0.25 equals negative square root of 1/2. We have pi sub 0.25 squared equals 1/2. We have to take the negative since we know that we're in the negative interval there, looking at the graph. So that's where the graph becomes pretty important in these solutions. So I have one more here where we're doing the, we're going to have to do integration by parts. I want to review this so that it refreshes what you do for integration by parts. We have x distributed as f of x, x times e to the negative x. And x goes from 0 to positive infinity. We want to find the moment generating function e of e to the tx. So that is going to be e to the tx times x, or f of x, and I forgot my dx. Please don't forget your dx. And since we're going to be proper about this, since this is infinity, we need to replace infinity with some constant b and then take the limit as b goes to infinity. And when we look at this integral, we say we can't do that, but we can use integration by parts. So we let u equals x so that we get rid of that x, and we can, if we get rid of the x, we can integrate this, right? So we want to take u equal to x so that we get rid of x by differentiating. And then we set the rest, e to the negative x 1 minus t dx equal to dv. So then we have to take the integral of that. We can integrate that. If you need to use u substitution for that, or any substitution you want, you might not want to use the letter u since you're using it over here. You can do that. And we get this expression. And then remember that the integral of u dv is equal to uv, if this is from a to b, evaluated from a to b, minus the integral from a to b of v du. I've done that here and worked through it. please, in particular, I'm going to skip down to this point here, but please walk through the whole thing. I have, well, actually, yeah. So I have taken the integral, and I end up with, I actually have negative b e to the negative b 1 minus t. And so I'm trying to put in infinity, but if I do that, this term goes to 0, and this term goes to negative infinity, and so that's an indeterminate form. So I've rewritten it so that I have a function on the bottom and a function on the top. I'm going to use L'Hopital's rule and take the derivative with respect to b in this case because it's the variable that's going to infinity. When I do that, I end up with a negative 1 on top, and then on the bottom, remember I don't have a negative when I put this on the bottom. So I take the derivative, I end up with this. When I put the limit, when I take the limit as b approaches infinity, this on the bottom goes to infinity, the whole thing goes to 0. So you have to be very careful here. You don't do this for 0 though. 0, if you plug in 0 here, you have 0. Because the top is 0, and then the bottom is e to the 0, which is 1. So for 0, x equals 0, we don't need L'Hopital's. So it's just 0 there. And then we do the same thing for this expression, but we don't need L'Hopital's because we only have 1b, and when we plug in for infinity there, we drive the whole thing to 0. And so we're left with this term here. And if you note that the only way that you can, that L'Hopital's works here is if this is a positive quantity on the bottom. And the only way that this exponent is a positive quantity is if 1 minus t is greater than 0, which means that t is less than 1, which is exactly what we have over here. So the interval converges. Once we have the moment generating function, we can find mu by taking its derivative. I've done that here. We go to here, we plug in 0. For t, we end up with 2. I did the same thing with sigma squared ex. I take the second derivative. I get this expression, and the second derivative at 0 is 6. And then I plug in for my ex squared minus ex quantity squared, and I get 2 for my variance. So please don't forget to scan in and upload your lecture notes before midnight of the date listed in the course calendar. You'll want to take your notes. I don't know that we updated anything that you need to update your distributions or your formula sheets, but if you feel like it, you're welcome to, of course. Open notes, open book test. Please come to our virtual office hours if you have questions. If not, email me, send me a picture of the problem and your work, and I'll be able to help you through email. Take care, and we will see you next time.